Welcome everybody to the first webinar from Intech Plastics on engineered plastics in modern data centers. My name is Mike Schaefer. I'm the commercial director here at Intech Plastics for our data center segment. And joining us is Levi Lesh.
Hi, my name is Levi Lesh, and I'm the principal engineer for manufacturing and materials innovation at Intech.
Thank you, Levi. So we'll begin with a brief introduction to Intech, a plastic solutions company. We've been around for over 50 years, primarily servicing the construction fenestration market, but also medical, lighting, aerospace, data center, power and infrastructure, many different segments. We are a plastic solutions company, so think beyond just extrusion, molding, and additive, but an all-encompassing resource and your in-house plastics experts. Why plastic? Why are we seeing this shift from traditional materials? Well, it offers some design flexibility and improved energy efficiency. It can be lighter, more durable, more corrosion and chemical resistant. We offer very precise tolerances and in many cases can be very cost effective when compared to traditional materials. We're seeing many manufacturers begin to look to plastics in places they had not previously. So to begin with, we'll talk about ratings and certifications to do with material selection. Selecting the right engineered plastic begins with identifying all required certifications. Many data center components must meet UL standards tied to electrical insulation, thermal performance, flammability. These certifications ensure materials can withstand that operational load safely, helps narrow the field of suitable materials, and avoids costly redesigns later. Once certifications are clear, the next step is usually selecting the polymer itself. Each polymer's molecular structure affects how it performs under thermal, mechanical, and environmental stresses. So some key questions to guide the decision include: where is the component being used? Is it structural, airflow, electrical insulation? Is it located in the hot aisle, the cold aisle? Those temperature deltas matter. And then, what temperature will it see in regular operation? Understanding that max-min temperature ensures that the material won't soften, creep, or crack. So this structured approach ensures compliance, performance, and really long-term reliability in data center applications. Up next in the discussion is thermal performance and material stability. Levi, would you chime in on this part of the design process?
Yeah, absolutely. So understanding the temperature range of a plastic material or the environment that it's going to be exposed to is really critical to ensuring that it meets the performance requirements in a data center environment. All plastics respond to temperature changes to varying degrees. At elevated temperatures, they can soften and deform, and at low temperatures, they can become brittle and might fracture. Selecting a material that maintains its key properties across the full operating range is essential. There's several ways that we measure the temperature resistance of a material. The heat deflection temperature is one of the most common. It is a quick and easy test and indicates the temperature at which a plastic deforms under constant pressure. It's a useful reference value for comparing materials. However, it's not sufficient to really define the full operating range for a material. The Vicat softening point is a similar test that assesses when a material begins to soften. Though compared to the heat deflection temperature, it's more of a surface level test. So when the material begins to soften, a probe is able to push into the surface of the material. The Vicat softening test is more useful for amorphous thermoplastics that don't have a clearly defined melt temperature, but instead soften gradually over a range of temperatures. The brittleness temperature of a material is designed to understand at what temperature a material goes from a tough and ductile state into a hard and brittle state, and is defined as the temperature at which half of the specimens fail under an impact test. And then the most robust of the thermal tests is called the RTI, or Relative Thermal Index. And this is a test that takes roughly 10,000 hours to complete, and it assesses the the temperature at which either strength or impact or electrical properties diminish by 50%. So together, all of these different tests can provide a comprehensive view of the short and long-term thermal performance of a material to help engineers select the right material for their environment.
Thank you, Levi. So let's talk a little bit about hot and cold aisle containment. So many of our plastics are extremely effective at separating hot and cold air streams in the data centers, and this is because they naturally exhibit low thermal conductivity. That means heat does not pass easily through them. So using ASTM D5930, we measure how heat moves through that material, often in plane and through plane, but plastics typically fall between zero point 0.1 and 0.4 watts per meter Kelvin. Common metals, just for reference, exceed 10 watts per meter Kelvin, and superconductors like aluminum or copper exceed 100 watts per meter Kelvin. So this massive difference makes plastics ideal for containment panels, louvers, ducts, and other structures that maintain strong separation between hot and cold aisles. Fillers can also play a role. They can either raise or lower conductivity depending on the formulation. This gives engineers a little bit more control over performance, and essentially good airflow separation directly improves energy efficiency, reducing cooling load, and supports these higher density rack designs. Our next slide is on the coefficient of thermal expansion. Levi, could you talk us through this one as well?
Yeah, absolutely. So coefficient of linear thermal expansion, or CLTE, is a somewhat more nuanced property, but nonetheless, it's really important for certain applications, particularly large components like containment panels, ducting, or any other long linear profile. The thermal expansion coefficient describes how much a plastic part grows or shrinks when it undergoes a temperature change. So when the temperature decreases, parts tend to shrink, and when the temperature increases, parts tend to get longer. So what does this mean? If the thermal expansion of a material is too high, you might get parts bending or bowing, and at lower temperatures, excessive shrinkage can cause gaps to form between components. This can compromise airflow control and water tightness, or it can compromise assembly fitment. In that vein, particularly when plastic components interface with other types of materials like metals and ceramics, and you have different rates of thermal expansion, you can really accumulate a lot of stresses in your parts. Certain fillers, such as glass fibers or mineral, when added to these plastics, can significantly reduce the thermal expansion coefficient and improve dimensional stability. There is a balance, however. If you add too much of these fillers to a plastic, they can become extremely brittle and break when subjected to excessive forces or impacts. So it's really a trade-off between the toughness and durability of your material versus that dimensional stability.
Perfect. Thank you, Levi. Next, we'll talk a little bit about dielectric performance, so electrical insulation. This is an area where Intech really excels. So dielectric performance refers to how a material behaves in the presence of an electrical field. This dielectric constant, also known as permittivity, describes a material's ability to store electrical energy. Permittivity is commonly measured in ASTM D150, and D2520 is often used when evaluating materials for electromagnetic interference or EMI performance. So another important part of this is the dissipation factor, which measures how much electrical energy is lost as heat while current flows through the material. In certain high frequency or high power applications, minimizing energy loss becomes critical. Many factors influence dielectric behavior, understanding polarity, moisture exposure, application requirements. These all help us select the right material for safe and reliable electrical performance. And Intech offers a number of different materials to use in these systems, and we're happy to talk you through all the different variables and options that exist. Flammability. Let's talk a little bit about understanding UL 94 ratings. Levi, can you talk us through this one as well?
I can take care of that one. So flammability testing for plastics is governed by a variety of standards, including ASTM and NFPA. But the one that's probably most familiar to people is UL 94. UL 94 evaluates the burning behavior of a material, and it looks at three primary criteria, those being how quickly or whether a material self-extinguishes, whether it produces flaming drips that ignite a cotton ball positioned below the test specimen, or whether the flame can burn through a material from one surface to another. So starting at the lowest end of the burn performance scale is HB, or horizontal burn. So as the name suggests, your specimen is oriented horizontally and a flame is applied, and the test evaluates how quickly or whether the flame is able to burn horizontally across the test specimen. And then in terms of increasing performance for a vertically oriented specimen, the lowest rating is V2, which denotes a material that may self-extinguish but would produce flaming drips of molten polymer that ignite the cotton ball. A V1 rating is for a material that self-extinguishes and might drip but doesn't ignite the cotton ball. And a V0 material would self-extinguish without any flaming drips. And this is a common requirement for electrical and power components that you might find in a data center. For the most demanding applications, you'd be looking at the 5V tests, of which there are 2 ratings. And this utilizes a specimen oriented horizontally with a flame applied underneath. For a 5VB specimen, you might have some surface damage or slight burn through. And for a 5VA rating, the specimen would resist burn through entirely. It's important to note that the flame source for the 5V tests is roughly 5 times more energetic than for the HB and the V0 tests. Some polymers, such as PVC, are inherently flame retardant, so they tend to do quite well under these assessments. For other polymers, such as polycarbonate and ABS, these will typically require the addition of flame retardant additives to improve their performance. These fillers can also compromise mechanical properties and thermal performance. So it's important to understand how these fillers interact with your plastic so that you're not compromising other performance requirements. And understanding this early in the design process is really critical to ensuring the safety, compliance, and long-term reliability of these components in your data center.
Absolutely. Thanks, Levi. So let's talk a little bit about sustainability and how this is more than just materials. So sustainability in data centers can mean different things depending on your perspective, and it's important to consider them all together. For some, sustainability starts with materials, whether it's a plastic is petroleum-based, bio-based, or may contain recycled content like PIR, PCR. It's post-industrial or post-consumer recycled. Others focus on life cycle considerations. This includes whether a product is recyclable, it's landfill degradable, home compostable, or designed to use in like a mono-material approach that supports single-stream recycling. Longevity also matters. Materials that last longer reduce replacement frequency and waste. A third and often overlooked dimension of this is operational sustainability. So in data centers, this means maximizing computational output while minimizing non-computational power draw. Materials that help maintain airflow separation, reduce weight, and support higher rack density directly contribute to energy efficiency and profitability. As data centers continue to scale in size and complexity, materials must also evolve alongside them. Engineered plastics offer compelling alternative to traditional materials by enabling lightweight, cost-effective, and really highly customizable solutions, but without sacrificing thermal, electrical, or mechanical performance. So, whether your goal is durability, compliance, insulation, sustainability, plastics can be engineered to meet the unique demands of that application. And partnering with Intech provides access to technical expertise and a collaborative team that's focused on delivering smarter and more sustainable data center options. So on the topic of applications, let's run through a short list of some of the places you can find our plastics within these data centers. First and foremost, we have hot and cold aisle containment panels. We talked about this a little bit previously, but twin wall polycarbonate is a very popular option for these containment panels, and we can offer that as well as fully assembled panels delivered to you within a 4-week lead time in some cases. Enhanced security can take the form of some diffusion additive added to these panels to hide what's behind them essentially. Busbar insulators and busway systems are very high dielectric strength plastic, can be used in these architectures. Ducts and louvers, cable management, all of the parts, the plastic parts and pieces that we find supporting these architectures are solutions we can help you with. So plastic parts may not be the most eye-catching technology in the data center, especially compared to some of the advanced cooling methods and high-power GPUs and emerging power solutions. But plastics are still a pretty critical part of the infrastructure, and it helps data centers run efficiently and reliably. So earlier in this webinar, we covered key polymer properties that matter in data center environments, and this section shifts from properties to more real-world use. We'll walk through some of the most common plastic components found in data centers and highlight the polymers that tend to be used in these applications. Our goal here is to connect material selection to practical outcomes, including safety, energy efficiency, and long-term performance. Hot and cold aisle containment. So with advancements such as direct-to-chip and immersion cooling, maintaining the effective separation between hot and cold aisles, hot and cold air streams remains a critical part of data center design. The temperature differentials between these zones can reach up to 60 degrees Fahrenheit. This makes material selection especially important. Our containment panels, must limit heat transfer while still allowing visibility and access. So oftentimes we find polycarbonate, PET, and acrylic are well suited for these applications. They offer low thermal conductivity, which helps preserve airflow separation while also providing transparency and design flexibility. Like I mentioned, we offer a standard twin wall polycarbonate that has become sort of a standard for use in these containment solutions, and we can assemble these to your custom size in as little as 4 weeks. Compared to traditional materials, these plastics reduce weight, improve impact resistance, and allow for custom panel geometries, which you can integrate more easily into your racks. Enhanced security. So in co-location data centers, multiple customers operate within the same facility, often in very close physical proximity. In these environments, visual security has become a pretty important consideration alongside airflow management. Containment panels can be manufactured with light diffusing additives or optical features that sort of obscure direct visibility into the racks and hardware. This just helps protect sensitive infrastructure and trade secrets, but without compromising airflow or access. Beyond the panels themselves, plastics enable more fully integrated containment system. Components of U-channels and adhesive aligned gaskets. It can help seal gaps, improve fit, maintain consistent performance across the entire assembly. So together, these plastic elements support both security and operational efficiency. This makes them especially valuable in shared data center environments. Busbar insulators. These play a critical role in the power delivery infrastructure of the data center. Primary function is to prevent dielectric breakdown and surface tracking from high voltage bus bars, helping protect both operators and nearby hardware. Because these components operate in close proximity to high electric loads, electrical insulation performance is essential. At the same time, busbar insulators must meet very strict flammability requirements, most commonly UL 94B0, to support overall fire safety. Widely used material for these applications is a PPO alloy known as Noril from Sabic or Xyron from Asahi. These materials combine excellent dielectric properties with self-extinguishing flame performance. These alloys are also hard and rigid, which makes them easier to handle and assemble, while also maintaining dimensional stability in demanding electrical environments. So this balance of electrical, thermal, and mechanical performance makes them a very strong choice for busbar insulation systems in modern data centers. Ducts and louvers. So these are another significant part of airflow management within data centers. We can find these installed directly on server racks. These components help guide air exactly where it's needed while maintaining insulation between hot and cold zones. Their ability to be adjusted allows operators to fine-tune air delivery and exhaust paths. It also supports cooling efficiency and more consistent thermal performance across the rack. Plastics are well suited for these applications because of their low thermal conductivity, which helps limit heat transfer to the component itself. Many duct and louver designs also incorporate a co-extruded rubber bulb seal, which adds just an extra layer of insulation and provides a little bit more flexible fit when mating to uneven surfaces. The combination of rigid and flexible PVC, for instance, allow manufacturers to integrate structure and sealing into a single component, improving performance and simplifying installation and long-term maintenance. Levi, we can, correct me if I'm wrong here, but we can extrude up to 4 different materials into one profile. Is that correct?
Yeah, that's absolutely right. So you can really tailor the exact function of your components by selecting, again, those 4 different materials or up to 4 different materials, so you get the right mix of stiffness and flexibility where you need it, good sealing properties, UV resistance, a rigid substrate that deforms less under temperature changes, etc.
Great, thank you. All right, we'll talk a little bit about cable management. So overhead cable trays and rack-mounted cable fingers are probably among the most visible plastic components in a data center. These systems play an important role in organizing and protecting power and data cabling, right? Cable management components are exposed to moderate mechanical loads as well as elevated ambient temperatures, particularly near high-density racks. So the materials used in these applications must maintain strength and shape over time. PVC is a commonly selected material for cable trays and cable fingers because it offers a strong balance of durability and thermal stability. It resists deformation, handles continuous load, and performs pretty reliably in warm environments. By using plastic materials instead of metal, these systems also benefit from reduced weight, corrosion resistance, and easier installation. This just supports long-term reliability in the data center operations. Okay, optimized conduit and pipes. So conduit and piping systems extend throughout the data center, often totaling miles in length, right? Because of that scale, even small design details can have significant impact on installation time, long-term reliability, and maintenance. Plastics such as PVC and polyethylene are well suited for these systems due to their low weight, corrosion resistance, and ease of handling compared to metal alternatives. Their low coefficients of friction and high abrasion resistance support smooth cable pull through. This reduces installation effort and just the risk of cable damage, really. Another critical feature of plastic conduit systems is how individual sections are joined. Proper joining allows separate lengths to be connected while maintaining a smooth internal pathway, minimizing hang-up points, and that can slow down installation or damage cables. For PVC systems, we often see solvent welding as a commonly used option. This creates strong watertight joints. Polyethylene systems are often joined using ultrasonic or spin welding. This produces a continuous uniform bond. These joining methods help create long, uninterrupted runs that support both performance and durability. These are both operations that Intech can perform in-house as a service for our customers. Together, material selection, joining methods make plastic conduit and piping systems a scalable and reliable solution for modern data center infrastructure. Lastly, here we have linear enclosures. So linear enclosures cover a pretty broad range of products designed to protect wires and cables and small electric devices as they travel along linear pathways through the data center. These enclosures also provide convenient access points for inspection, maintenance, future upgrades, which makes durability especially important. Because linear enclosures are installed in many different locations, they must perform reliably across hot and cold environments. So resist impacts and withstand ongoing wear without cracking or deforming. Engineering thermoplastics such as ABS and polycarbonate are well suited for these applications. They offer a strong balance of toughness and temperature resistance and dimensional stability. This makes them very reliable materials for protecting your critical infrastructure. Partnering with Intech Plastics. So why Intech? We have decades of extrusion and molding experience. We have a very deep material expertise. We have a robust supply chain, and we have a team built around data center environments. So with that, you get complete solutions, engineered plastic components, scalable custom solutions, and a reliable long-term performance partner.